And now in this lecture we'll answer 2 questions. The first question, we find out the area of this circle that is inscribed by this trapezoid ABCD. And in the second question, we find out the length of this line segment QB is equal to x. So we start with the first question. In the drawing, we have this circle that is inscribed by this trapezoid ABCD. You know that this is line segment AM, that is equal to A units in its length. This is line segment MB, that is equal to B units in its length. Again, our mission is to find out the area of this circle that is inscribed by this trapezoid ABCD. So first of all, we define the center of this circle. This point is point O. We define the point of tendency of tangent AD with this circle. This point is point P. And we define the point of tendency of this tangent BC with this circle. This point is point Q. So here we can implement rule 2. So I put quickly on rule 2. According to rule 2, the lengths of two tangents for a common start point per circle are equal. In the drawing we have a circle, and this is the common start point, point P. From this common start point, point P, we have two tangents to this circle, tangent PA and tangent PB. And according to this rule 2, the length of tangent PA is equal to the length of tangent PA. Again, PA equals to PB according to this rule 2. So we can actually implement rule 2 in our drawing. We put in our drawing, if we focus on this common start point, point A, on this common start point, point A, we have two tangents to this circle, tangent AP and tangent AM. And according to rule 2, they are equal to each other. That is to say, AM equals to AP. But AM equals to A. Therefore, AP must be also equal to A units in its length according to rule 2. So AP equals to A units in its length. Likewise, according to the same rule, if we focus on this common start point, point B, on this common start point, point B, we have two tangents to this circle, tangent BM and tangent BQ. And according to rule 2, they are equal to each other. That is to say, BM equals to BQ, but BM equals to B, according to what is given as the question. Therefore, BQ must be also equal to B units in its length. So I write it down. This is tangent BQ that is equal to B units in its length according to rule 2. In the next step, we will join point O is the center of this circle. Okay, so we join points O and Q together by a straight line. Point O is the center of this circle, point Q is the point of the circle itself. Therefore, OQ is the radius of this circle. We define the radius of this circle as x, so OQ equals to x, it is the radius of the circle. And because of the fact that the radius OQ is equals to x, the radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle, and whenever you have a radius that is drawn to the point of tendency, then according to rule 1, tangent BC will be perpendicular to the radius QO. If BC is perpendicular to QO, it means that this angle equals to 90 degrees, And this angle also equals to 90 degrees according to rule 1. Likewise, we join points O and P together by straight line. OP is of course the radius of this circle, that is equals to x, so OP equals to x. And because of the fact that the radius OP is equals to x, the radius OP is drawn to point P, that is the point of tendency of tangent AD with this circle. And remember, you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees. And this angle also equals to 90 degrees according to the same rule 1. In the next step, we will do a construction. That is to say, from this point A, we will draw perpendicular on BC. Again, from point A, we will draw perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point N. By doing this construction, we can do those two angles. Those two angles, they are both defined as one-sided interior angles, and they are located between the parallel lines AD and BC. Why side AD is parallel to side BC? Because of the fact that ABCD is a trapezoid, and we know that in any trapezoid, a trapezoid is a quadrilateral with one pair of parallel sides. Again, a trapezoid is a quadrilateral of one pair of parallel sides. In this trapezoid ABCD, side AD is parallel to side BC. So side AD is parallel to side BC. So those two angles, they are both defined as one-sided interangles, and they are located between the parallel lines AD and BC, and according to rule 17, the sum of two one-sided interangles that are located between parallel lines is equal to 180 degrees. So I repeat quickly on rule 17. According to rule 17, the sum of one-sided interangles that are located between two parallel lines is equal to 180 degrees. So in the drawing we have line A that is parallel to line B. Those two angles are both defined as one-sided interangles. And because of the fact that those two angles, alpha and beta, that are defined as one-sided interangles, they are both located between the parallel lines A and B. Therefore, according to this rule 17, the sum of those two one-sided interangles is equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. So, as I already mentioned, you can implement rule 17 in our drawing. In our drawing, we have those two angles. They are both defined as one-sided interangles, and they are located between the parallel lines AD and BC. And therefore, according to rule 17, the sum of those two one-sided interangles is equal to 180 degrees. But this is the right angle, it is equal to 90 degrees in its size according to our construction. So 90 degrees plus this missing angle, in total the sum of those two angles must be equal to 180 degrees. So this missing angle must be equal to 90 degrees in its size. Only all 17, of course. In the next step, we will do another construction. That is to say, from this point O, that is the center of this circle, we will draw perpendicular on AN. Again, from point O, we will draw perpendicular on AN. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. When you find the touching point of the perpendicular from point O and AN, this point is point T. But doing this construction, we created this small quadrangle APOT. Inside this quadrangle APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle. In total, they must be equal to 360 degrees according to the rule that states that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. Likewise, we'll focus on this small quadrilateral, the lower small quadrilateral TOQN. Inside this small quadrilateral TOQN, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this fourth missing angle, in total they must be equal to 360 degrees according to the formula that I mentioned, that the sum of the angles in any quadrilateral is equal to 360 degrees. Therefore, this fourth missing angle must be equal to 90 degrees in its size. So the big angle POQ equals to 90 degrees plus 90 degrees, that is 180 degrees. So angle POQ is equal to 180 degrees in its size, and we know that any angle that is equal to 180 degrees in its size must be a straight line. Therefore, line segment POQ must be a straight line. So angle POQ is equal to 180 degrees, and therefore line segment POQ is a straight line. If POQ, this line segment, is a straight line, PQ is also a straight line. Again, PQ must be also a straight line. So I have to know PQ, line segment PQ is also a straight line. So actually, this is shape APQN. Again, this is shape APQN. So in this shape APQN, we have 1, 2, 3, 4 sides. Again, in this shape APQN, we have 1, 2, 3, 4 sides. So if you know, in shape APQN, we have four sides. Therefore, shape APQN is a quadrilateral. Why? Because it has four sides. So, shape APQN is a quadrilateral. But quadrilateral APQN has four right angles. And according to rule 5, any quadrilateral that has 4 right angles must meet this rectangle plus a square. So we relate to this quadrilateral APQN as a rectangle because it has 4 right angles. So as you know, quadrilateral APQN is a rectangle because it has 4 right angles. So as you know, this is quadrilateral APQN and it is a rectangle according to rule 5. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APQN, side AP must be equal to the opposite side QN. But AP is 8, therefore the opposite side QN must be also equal to A units in its length. Likewise, according to the same rule, in the same rectangle APQN, side PQ must be equal to the opposite side AN. But PQ in total equals to x plus x, that is 2x, therefore the opposite side AN must be also equal to 2x units in its length. So the opposite side AN is equal to 2x units in its length. This is the opposite side AN that is equal to 2x units in its length. What is the length of the missing 9 segment BN? BN equals to BQ minus NQ. Again, BN equals to BQ minus NQ. So I write it down. BN equals to BQ minus NQ. So BN in total is equal to BQ. BQ according to rule 2, BQ equals to B minus NQ. NQ equals to A. So in total we found out that the length of the missing side BN is equal to B minus A units in its length. So BN equals to B minus A units. Side AB, again, this is side AB. Side AB in total equals to A plus B. Again, AB in total equals to A plus B. So in the next step, I will copy the right triangle A and B in a new page, and we'll implement the Pythagoras theorem on this right triangle A and B. According to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. Here by PT is the progression for Pythagoras theorem. Side AN of the right triangle NB equals to 2x units in its length. Side NB equals to B minus A units in its length. And the hypotenuse AB equals to A plus B. So actually, this is the right triangle A and B that I go into the original drawing. This right triangle A and B, AB squared, that is the square of the hypotenuse, is equal to AN squared plus BN squared. So I write it down. So AB squared, that is the square of the hypotenuse, is equal to AN squared plus BN squared. The hypotenuse AB equals to A plus B, therefore AB squared is A plus B squared, and it is equal to AN squared. AN is 2x, therefore AN squared is 2x squared. That is actually 2x squared is 2 squared, that is 4 times x squared, that is x squared. So in total 2x squared is 4x squared plus Bn squared. Bn is B minus A, therefore Bn squared is B minus A squared. So in total, according to the Pythagoras theorem, in the entire BA, we should find out that A plus B squared equals to 4x squared plus B minus A squared. Here we'll open the brackets on both sides of this equation and get that A plus B squared equals to A squared plus B squared plus 2 times A times B, and it is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus A squared minus 2 times A times B. So here we have A squared on both sides of this equation, so A squared gets cancelled. And we have also B squared on both sides of this equation, so B squared also gets cancelled. After we cancel those two expressions, on this side of the equation we left only with 2AB. On the other side of this equation we left with 4x squared minus 2AB. So here we add 2AB to this equation, and we get that 2AB plus 2AB is 4AB. So 4AB equals to 4x squared. Here we divide this equation by 4 and get that 4AB over 4 is AB, and it equals to 4x over 4 is x squared. So in total, if you found out that x squared equals to AB. X squared equals to AB. Our mission is to find out the area of this circle that is described by this trapezoid ABCD. Actually, we know that the area of any circle is equal to pi times the radius of the circle squared. Repeat again. We know that the area of any circle is equal to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total, if we found out the area of this circle, that is the area that we are looking for in this question, is equal to pi times x squared. But we just right now found out that x squared equals to AB. So we substitute x squared in this equation by AB, and we get that in total the area of our circle is equal to pi times x squared, and x squared is AB. So in total, if you found out that the area of this circle is equal to pi times AB square units. So repeat again, the area of this circle is equal to pi times AB square units. So we finish with the first question. In the next step, I present to you the second question and also on the second question of this lecture. So, our mission in this second question is to find out the length of this line segment QB that is equals to x. We have to find out the value of x. Okay, so in the drawing, we have a semicircle. This is a semicircle. Inside this semicircle, we have this chord AP that is equals to 10 units in itself. Also have this chord PQ that is also equals to 10 units in itself. AB. AB, that is the diameter of this semicircle, is equal to 30 units in its length. Again, our mission is to find out the length of this line segment QB that is equal to x. We have to find out the value of x. So in the first step, we define the center of this semicircle. This point is point O. We know that the diameter of this semicircle AB equals to 30 units in its length. If the diameter is equal to 30, the radius of this semicircle must be equal to half of it. That is to say, the radius of this semicircle must be equal to 30 over 2, that is 15. The radius of this semicircle equals to 15 units in its length. Always, the radius of this semicircle, that is equal to 15. OB is also the radius of this semicircle, that is also equal to 15. In the next step, we complete this semicircle to a circle. And we'll join points O and P together by straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle that equals to 15 units in its length. In the next step, we'll extend the radius PO by a straight line until it touches the circle. So this is the touching point of the extended radius PO with this circle. So we define this touching point. This point is M. Point O is the center of the circle. Point M is the point on the circle itself. Therefore, OM is the radius of this circle. This is also equals to 15 units in its length. So in the next step, we join points B and M together by a straight line. This is angle AOP. Again, this is angle AOP. Angle AOP is defined as vertex angles. This is angle BOM. Angle BOM also defined as vertex angles. And we have the rule that vertex angles are equal to each other. That is to say, those two vertex angles are equal to each other. So if we define the side of this vertex angle AOP is theta, then this vertex angles MOB must be also equal to theta, according to the rule that the vertex angles are equal to each other. So in the next step, we'll prove that triangle AOP can go into triangle MOB. But again, we prove that those two triangles can go into each other. So this is triangle AOP. And we prove that this triangle AOP can go into this triangle MOB. Okay. So why those two right triangles? They are not right triangles. Why those two triangles can go into each other? First of all, side OP equals to side OM. They are both the radii of the circle, therefore they are equal to each other. Each of them is equal to 15 units in its length. So side OP, this is side OP in triangle AOP, is equal to side OM in this triangle MOB. Number the area of the circle that is equal to 15 units in its length, therefore they are equal to each other. Read again, if you found out that side OP of triangle AOP is equal to side OM of triangle MOB, above the area of the circle that is equal to 15 units in its length, therefore they are equal to each other. In addition, as I already mentioned, we have those two vertex angles, and we know that vertex angles are equal to each other. So actually, this is angle AOP. In triangle AOP, and it is equal to this angle, that is actually angle MOB. In triangle MOB, they are both equal to theta, therefore they are equal to each other according to the rule that vertex angles are equal to each other. And finally, this is side AO in triangle AOP. This is equal to this side OB in triangle MOB. They are both the area of the circle that is equal to 15 units, therefore they are equal to each other. So side AO in triangle AOP is equal to side OB in triangle MOB. Above the area of the circle that is equal to 15, and therefore they are equal to each other. So if you found out that those two triangles can go into each other according to side angle side rule. So write it down. If you found out that triangle AOP congruent, this is the sign of congruent, to triangle MOB according to side angle side rule. I'll explain what I mean. If you found out that those two sides and the angle that is included between those two sides, that is theta, this triangle AOP are correspondingly equal to those two sides, and the angle that is included between those two sides that is also angle theta, and triangle OMB. Therefore, those two triangles can go into each other according to side angle side rule. We have two sides and the angle that is included between those two sides in triangle AOP are correspondingly equal to those two sides, and the angle that is included between those two sides that is also angle theta in triangle MOB. Therefore, those two triangles can go into each other according to side angle side rule. And from the fact that those two triangles can go into each other, we derive that side AP of the right triangle AOP is equal to side MB of the right triangle MOB. Again, side AP of the triangle AOP is equal to side MB of triangle MOB according to the rule that corresponding sides and congruent triangles are equal to each other. Those two triangles can go into each other, therefore those two corresponding sides, that is to say AP and MB, must be also equal to each other. But AP equals to 10 units in itself, it's only what is given as a question. So you can write here that AP equals to 10, and from this equation 10 equals to AP equals to MB, we will derive that MB is also equal to 10 units in its length. Okay, MB is also equal to 10 units in its length. So this is side MB that is equal to 10 units in its length. This is line segment PM. Line segment PM passes through point O that is actually it is chord PM. Chord PM passes through point O, that is the center of the circle, and you know that any chord that passes through the center of the circle must be the diameter of the circle. So chord PO passes through point O, that is the center of the circle. Therefore chord PM is the diameter of this circle. So in the next step, I'll copy this semicircle with the diameter PM, and we'll analyze this semicircle with the diameter PM. So here, this is the semicircle with the diameter PM that I copied from the original drawing. So in the next step, we'll extend side A and B and side PQ by straight line until they touch each other. So here, this is their touching point, so we define this touching point as E. So by doing this construction, create a triangle PEM. This is triangle PEM. Line segment PQ equals to line segment MB. And we extended those two equal line segments by straight line. And therefore, QE must be also equal to BE. QE must be also equal to BE. So if QE is Y, then BE must be also equal to Y because they are equal to each other. So side PE in total equals to 10 plus Y. And side ME also equals to 10 plus Y. So if you found out that side PE is equal to side EM in this triangle, triangle PEM. Side PE is equal to side EM in triangle EPM. Again, side PE equals to side EM in this triangle, triangle EPM. And we have the rule that says that in front of equal sides in the triangle there are equal angles. So in front of this side EP we have this angle, that's angle EMP. And in front of this side EM we have this angle, that's actually angle MPE. And those two angles that are located in front of those two equal sides must be also equal to each other in their sizes. So if we define the size of this angle MPE as beta, then the size of this angle PME must be also equal to beta according to the rule that I mentioned. Okay, so we have here this semicircle blocks quadrangle PQBM, and again this semicircle blocks this quadrangle PQBM. If we complete this quadrangle, if we complete this semicircle to a circle, then this quadrangle PQBM will be inscribed by a circle. Again, if we complete this semicircle to a circle, this quadrangle PQBM will be inscribed by a circle. And we have the rule that says that if a quadrangle is inscribed by a circle, exactly like here, then its opposite sides is equal to 180 degrees. So this quadrangle is inscribed by a circle, and therefore the sum of its opposite sides must be equal to 180 degrees. So I put quickly on the rule. So according to the rule that I mentioned, if a quadrangle is inscribed by a circle, then the sum of its two opposite sides is equal to 180 degrees. So in the moment we have a circle, and this is quadrangle ABCD. This quadrangle ABCD is inscribed by a circle, and therefore according to this rule, the sum of its two opposite angles is equal, the size of its two opposite angles must be equal to 180 degrees. That is to say, those are the two opposite sides in quadrangle ABCD, and according to this rule, the sum of its two opposite angles must be equal to 180 degrees. That is to say, alpha plus beta is equal to 180 degrees. Likewise, the other opposite angles of this quadrangle ABCD, and according to this rule, the sum of its two opposite angles is equal to 180 degrees. That is to say, angle 1 plus angle 2 must be also equal to 180 degrees in their sizes. So actually, according to the rule that I presented to you, the sum of those two opposite angles must be equal to 180 degrees, while because of the fact that this quadrangle PQBM is inscribed by a circle. If we complete the semicircle to a circle, this quadrangle PQBM is inscribed by a circle, and according to the rules that I mentioned, the sum of the opposite sides, the sum of the two the opposite sides of the angles of a quadrangle that is inscribed by a circle is equal to 180 degrees. So those are the two opposite angles inside quadrangle PQBM, and the sum of those two opposite angles must be equal to 180 degrees because of the fact that this quadrangle PQBM is inscribed by a circle. But this angle equals to beta, so this angle beta plus this missing angle, in total must be equal to 180 degrees according to the rule that I mentioned. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because of the fact that 180 degrees minus beta plus beta is equal to 180 degrees. That is the sum of the angles inside this quadrangle that is described by a circle exactly like this drawing. Likewise, the sum of those two opposite angles inside quadrangle PQBM must be also equal to 180 degrees according to the rule that I mentioned. But this angle equals to beta. So this angle that is beta plus this missing angle in total must be equal to 180 degrees according to the rule that I mentioned. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is equal to 180 degrees. that is the sum of the opposite angles inside quadrangle PQBM that is described by a circle. So if you found out that this is angle beta and this angle equals to 180 degrees minus beta. So 180 degrees minus beta plus beta, the sum of those two angles is equal to 180 degrees. Again, 180 degrees minus beta plus beta is 180 degrees. So we found out that the sum of those two angles is equal to 180 degrees. But those two angles are defined as one-sided interangles. So we found out that the sum of those two one-sided interangles is equal to 180 degrees. And therefore, according to rule 18, those two one-sided interangles that their sum is 180 degrees must be located between parallel lines. That is to say, here QB must be parallel to PM because of the fact that the sum of those two one-sided interangles is equal to 180 degrees. So repeat again on rule 18. According to rule 18, if the sum of two one-sided interangles is equal to 180 degrees, then they are located between two parallel lines. So in the drawing, we have line A and line B. This is line C that intersects with those two lines A and B and those 2 points. In addition, we have those two angles, alpha and beta. Those two angles, alpha and beta, are defined as one-sided interangles, and we know that alpha plus beta is equal to 180 degrees. Again, we know that alpha plus beta is equal to 180 degrees, and because of the fact that those two one-sided interangles, the sum of those two one-sided interangles is equal to 180 degrees, that is to say alpha plus beta is equal to 180 degrees. Therefore, those two one-sided interangles must be located between parallel lines. And they are located between lines A and B. And therefore, line A must be parallel to line B. Again, because of the fact that those two one-sided interangles, the sum of those two one-sided interangles is equal to 180 degrees, therefore, those two one-sided interangles must be located between parallel lines. That is to say, line A is parallel to line B. As I already mentioned, we can implement rule 18 in our drawing. Why? Because in our drawing, those two one-sided interangles, the sum of those two one-sided interangles is equal to 180 degrees. Why? Because 180 degrees minus beta plus beta is 180 degrees. So the sum of those two one-sided interangles is equal to 180 degrees, and therefore, according to rule 18, they must be located between parallel lines. They are located between line QB and line PM. And therefore, according to rule 18, line QB must be parallel to line PM. Again, according to rule 18, line QB must be parallel to line PM. So write it down. QB is parallel to PM according to rule 18. So repeat again, because of the fact that those two one-sided interangles, the sum of those two one-sided interangles is equal to 180 degrees, those two one-sided interangles must be located between parallel lines. But those two one-sided interangles are located between QB and PM. Therefore, QB must be parallel to PM according to rule 18. And again, QB must be parallel to PM according to rule 18. So, in the next step, I'll copy again this semicircle with diameter PM and we continue to analyze this semicircle. Therefore, this is the semicircle with diameter PM that occurs from the original drawing. Point O is the center of this semicircle. PM equals PQ equals to 10 units in its length according to what is given in the question. QB equals to X, that is the line segment that we are looking for in this question, and BM equals to 10. The next time we will join points Q and O together by a straight line. QO is of course the radius of this semicircle that is equal to 15 units in its length. We will also join points O and B together by a straight line. Point O is the center of the semicircle, point B is the point on the semicircle itself, therefore OB is the radius of this semicircle that is equal to 15. Likewise, OP is also the radius of the semicircle that is equal to 15. And finally, OM is also the radius of this semicircle that is equal to 15 units in its length. According to rule 18, QB is parallel to PM. We just find out that QB is parallel to PM according to rule 18. Actually, those two angles this is angle POQ and this is angle OQB. They are defined as alternating angles and they are located between the parallel lines QB and PM. Again, those two angles are defined as alternating angles and they are located between the parallel lines QB and PM, and therefore, according to rule 15, they are equal to each other in their sizes. Those two angles must be equal to each other in their sizes according to rule 15. So, I'll fit quickly on rule 15. According to rule 15, alternating angles between parallel lines are equal to each other. So, in the drawing, we have line A that is parallel to line B, and those two angles alpha and beta are defined as alternating angles, and because of the fact that those two alternating angles alpha and beta are located between the parallels A and B, therefore they must be equal to each other in their sizes. That is to say, angle alpha equals to angle beta. So we can implement rule 15 in our drawing. Why put in our drawing QB is parallel to PM. And those two angles also defined as alternating angles and they are located between the parallels QB and PM. And therefore they must be equal to each other in their sizes. So actually this is angle POQ, and it must be equal to this angle, that is actually angle OQB. OQB. So those two alternate angles are equal to each other according to rule 15. So if we define this angle as beta, then this angle must be also equal to beta because they are equal to each other according to rule 15. So actually we define this angle as alpha. So this angle equals to alpha, then this angle must be also equal to alpha according to rule 15. Okay, here we have angle alpha equals to POQ equals to angle OQB. So from this equation we derive that angle OQB is also equals to alpha. This is angle OQB, this is also equals to alpha. So in the next step I present to you the law of cosines, and we implement the law of cosines in this great triangle POB, and then we also implement the law of cosines in this triangle OQB. So what is the law of cosines? Actually, the law of cosines is true in any triangle. So actually, this is triangle ABC, that could be any triangle. And again, this is triangle ABC, that could be any triangle. We know that the length of this side AB is A units. Again, side AB equals to A units in its length. This is side AC, and the length of this side AC is equal to B units. And finally, this is side BC, and this side BC is equal to C units in its length. Repeat again, side AB equals to A units, side AC equals to B units, this is side BC, that is equal to C units in its length. This is angle BAC, that is equal to theta. Okay. This is the law of cosines. And according to the law of cosines, cosine theta is equal to A squared plus B squared minus C squared over 2 times A times B. And again, according to the law of cosines, in this triangle ABC, with this angle theta, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So this triangle ABC could be any triangle, therefore the law of cosines is true in any triangle. Okay? So in the next step I copy the great triangle, this triangle OPQ new page, and we implement the Pythagoras theorem on this great triangle OPQ. This is angle alpha. PQ equals to 10 units in its length. This is angle alpha. So according to the law of cosines, this triangle OPQ, that according to the original drawing, this is the green triangle OPQ, and this is the green triangle OPQ, the point here. So in this triangle OPQ, according to the law of cosines, this will be equation 1. Cosine alpha equals to 15 square plus 15 square minus 10 square divided by 2 times 15 times 15. So I copy equation 1 in a new page. According to the law of cosines, cosine alpha is equal to 15 square plus 15 square minus 10 square over 2 times 15 times 15. In the next step, we copy this triangle, the white triangle QOB in a new page, that will implement the law of cosines in this triangle, triangle QOB. So actually, this is triangle QOB that according to the original drawing. In this triangle QOB, this is angle alpha. In this triangle QOB, according to the law of cosines, this will be equation 2. Cosine alpha is equal to 15 square plus x square minus 15 square over 2 times 15 times x. Repeat again, according to the law of cosines, in this triangle OQB, cosine alpha equals to 15 square plus x square minus 15 square over 2 times 15 times x. So we have two different equations for the value of cosine alpha. So in the next step, we define equation 3 that says that cosine alpha, according to equation 1, must be equal to cosine alpha according to equation 2. And again, according to equation 3, cosine alpha according to equation 1 equals to cosine alpha according to equation 2. Cosine alpha according to equation 1 is equal to 15 square. This is cosine alpha according to equation 1. It is equal to 15 square plus 15 square minus 10 square over 2 times 15 times 15. This is equation 3. So cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. This is cosine alpha according to equation 2. So cosine alpha according to equation 2 equals to 15 square plus x square minus 15 square divided by 2 times 15 times x. Again, this is equation 3, that means that cosine alpha according to equation 1 equals to cosine alpha according to equation 2. So we have here, if we focus on the denominator of those two expressions, in both the denominators we have 2 times 15. So 2 times 15 will get cancelled. So in this side of equation 3 we have 15 square minus 15 square. 15 square minus 15 square is of course 0, so those two numbers also get cancelled. So in total we found out that in this side of equation 3 we have x squared over x. X squared over x is of course x. So we found out that x equals, here we have 15 square plus 15 square minus 10 square divided by 15. So in total, according to equation 3, we actually found out that x is the line segment that we are looking for, is equal to 15 square plus 15 square minus 10 square divided by 15. So according to equation 3, x equals to 15 square is 225, so 225 plus 225 is 450, minus 10 square. 10 square is 100, so it is minus 100 over 15. So in total, x equals to 450 minus 100 is 350 divided by 15. So here we divide both the numerator and the denominator of this number by 5, and we get that 350 over 5 is 70, and 15 over 5 is 3. So in total we found out that x equals to either 70 over 3 units in its length. In terms of numbers, 70 over 3 is 23 and 3 units in its length. That is the answer to the second question. And again, we found out that the length of this line segment qubit that is equal to x, it is equal to either 70 over 3 units. In terms of numbers, the length of qubit that is equal to x is equal to 23 and 3 units in its length. So finish with the second question. In the next step, I'll summarize the lecture. We'll start with the first question, of course. In the first question, our mission was to find out the area of this circle that is described by this trapezoid ABCD. So, in the drawing we have trapezoid ABCD that blocks this circle, and you know that this is line segment AM, that is equal to A units in its length. This is line segment MB that is equal to B units in its length. And our mission is to find out the area of this circle that is described by this trapezoid ABCD. I remind you that the definition of a trapezoid is a quadrilateral with one pair of parallel sides. In this trapezoid ABCD, side AD is parallel to side BC. Again, our mission is to find out the area of this circle. So first of all, we define the center of this circle. This point is point O. We define the point of tendency of this tangent AD with this circle. This point is point P. And finally, we define the point of tendency of tangent BC with this circle. This point is point Q. So here we can implement rule 2. If we focus on this common external point A, from this common external point A, we have two tangents to this circle, tangent AP and tangent AM. And according to rule 2, they are equal to each other. That is to say, AP equals to AM. But AM equals to A units in its length, according to what is given as a question. Therefore, AP must be also equal to A units in its length. Likewise, according to the same rule, if you focus on this common external point B, from this common external point B, we have two tangents to this circle, tangent BQ and tangent BM, and according to rule 2, they are equal to each other. That is to say, BQ equals to BM. But BM equals to B units in its length, according to what is given as the question. Therefore, BQ must be also equal to B units in its length. In the next step, we join points O and Q together by straight line. OQ is of course the radius of the circle, because point O is the center of the circle. We define the radius of this circle as x, so OQ equals to x, and because of the fact that the radius OQ that is equal to x, the radius OQ is drawn to point Q, that is the point of tendency of tangent BC with this circle. Whenever you have radius that is drawn to the point of tendency, then tangent BQ will be perpendicular to the radius QO. If BQ is perpendicular to QO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to rule 1. Likewise, we join points O and P together by straight line. OP is of course the radius of this circle that is equals to x, according to our definition. And because of the fact that the radius OP is drawn to point P, that is the point of tendency of tangent AD with this circle, whenever you have a radius that is drawn to the point of tendency, then tangent AD will be perpendicular to the radius PO. If AD is perpendicular to PO, it means that this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to the same rule, rule 1. In the next step, we did the construction, that is to say, from this point A, we do perpendicular on BC. Again, from point A, we do perpendicular on BC. So actually, this angle equals to 90 degrees, and this angle also equals to 90 degrees, according to our construction. We define the touching point of the perpendicular from point A and BC. This point is point A. It's point N. So, by doing this construction, we can do here those two angles. Those two angles are located between the parallels AD and BC. Again, side AD is parallel to side BC because of the fact that ABCD is a trapezoid. So, those two angles are defined as one-sided interangles, and they are located between the parallels AD and BC. And therefore, according to Rule 17, the sum of those two one-sided interangles that are located between the parallels AD and BC must be equal to 180 degrees. But this angle equals to 90 degrees inside, so 90 degrees plus this missing angle, in total the sum of those two angles must be equal to 180 degrees according to Rule 17. Therefore, this missing angle must be equal to 90 degrees in its side according to Rule 17. In the next step, we did another construction, that is to say, from point O, that is the center of the circle, we draw perpendicular on AN. Again, from point O, we draw perpendicular on AN. So this angle equals to 90 degrees, and this angle also equals to 90 degrees according to our construction. We define the touching point of the perpendicular from point O and AN. This point is point T. By doing this construction, we can then here the small quadrilateral APOT. Inside this small quadrilateral APOT, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of this 4 pieces again is in total they must be equal to 180 degrees according to the rule that said side quadrangle OP 80 we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of these 4 pieces again in total they must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, these 4 pieces again must be equal to 90 degrees in its size. Likewise, if we focus on the lower quadrangle TOQB, inside this quadrangle TOQB, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. So 270 degrees plus the size of these 4 pieces again in total must be equal to 360 degrees according to the rule that says that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, this 4 pieces again must be equal to 90 degrees in its size. So if we found out that the size of the big angle POQ is equal to 90 degrees plus 90 degrees, that is 180 degrees. So angle POQ equals to 180 degrees in its size. And we know that angle POQ equals to 180 degrees in its side, and we know that any angle that is equal to 180 degrees in its side must be a straight line. Therefore, POQ, line segment POQ is a straight line. Line segment POQ is a straight line because angle POQ equals to 180 degrees. So, if POQ is a straight line, then PQ must be also a straight line. PQ is also a straight line. So, in shape APQN, this shape APQN, we have 1, 2, 3, 4 sides. Again, in shape APQN, we have 4 sides. Therefore, shape APQN must be a quadrilateral because it has 4 sides. So in quadrilateral APQN, we have 4 angles. Inside quadrilateral APQN, we have 4 angles. And because of the fact that quadrilateral APQN has 4 angles, according to rule 5, any quadrilateral that has 4 angles must be a rectangle if not a square. So we refer to this quadrilateral APQN as a rectangle because it has 4 angles. But we also know that the opposite sides of a rectangle are equal to each other. So in rectangle APQN, side AP must be equal to the opposite side QN. But AP is A, therefore QN must be also equal to A units in its length. Likewise, according to the sum rule, in the sum rectangle APQN, side PQ must be equal to the opposite side AN. But PQ is x plus x, that is 2x, therefore AN must be also, the opposite side AN must be also equal to 2x units in its length. What is the length of the missing line segment BN? BN equals to BQ minus NQ. Again, BN equals to BQ minus NQ. So BN equals to BQ. BQ is B minus NQ. NQ is A. So in total, BN equals to B minus A units in its length. Again, this line segment BN equals to B minus A units in its length. AB in total equals to AM plus MB. So AB in total equals to A plus B. So in the next step, I complete the right triangle A and B in a new page and implemented the Pythagoras theorem on this right triangle A and B. So okay, according to the Pythagoras theorem, in any right triangle, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. This is the right triangle A and B that I go between the original drawing. In this right triangle A and B, AB squared, that is the square of the hypotenuse, equals to AN squared plus NB squared. AB is A plus B, therefore AB squared is A plus B squared, and it is equal to AN squared. AN is 2x, therefore AN squared is 4x squared, and this equals to NB squared. NB is B minus A, therefore NB squared is B minus A squared. So in total, according to the Pythagoras theorem, in this side and B, A plus B squared equals to 4A squared plus B minus A squared. Here open the brackets on both sides of this equation, and find out that A plus B squared equals to A squared plus B squared plus 2 times AB. And it is equal to 4x squared plus B minus A squared. B minus A squared equals to B squared plus a squared plus 2 times a times b. We have a squared on both sides of this equation, so a squared will get cancelled. We have b squared also on both sides of this equation, so b squared also will get cancelled. After we cancel those two expressions, in this side of this equation we left only with 2ab, in the other side of the equation we left with 4x squared plus 2ab. So in total we have found out that 2ab equals to 4x squared plus 2ab. Here we added 2ab to this equation, and we found out that 4x squared equals to 2ab plus 2ab is 4ab. So 4ab equals to 4x squared. Here we divided this equation by 4, and we found out that ab equals to x squared. ab equals to x squared. Our mission is to find out the area of this circle. Actually, note that the area of any circle equals to pi times the radius of the circle squared. Again, the area of any circle equals to pi times the radius of the circle squared. And therefore, the area of this circle must be equal to pi times the radius of this circle squared. The radius of this circle is x, therefore the radius squared is x squared. So in total, the area of this circle must be equal to pi times x squared. But x squared is ab. So we substitute x squared by ab in this equation. And find out that the area of this circle, that is the area that we are looking for in this equation, it is equal to pi times ab square units. Again, the area of this circle equals to pi times ab square units. So we finish with the first question. And let's have a presented to the second question and solve the second question of this lecture. Our mission in this second question is to find out the length of this line 7 cubic that is equal to x. We have to find out the value of x. So in the original drawing we have here a semicircle. Inside this semicircle we have line segment A or chord AP that is equal to 10 units in its length. We also have chord PQ that is also equal to 10 units in its length. And we have this chord QB that is equal to x. And we have to find out the length of this chord QB that is equal to x. We have to find out the value of x. In addition, we know that AB, that is the diameter of this semicircle, is equal to 30 units in its length. If the diameter is 30, the radius must be equal to half of it. That is to say, the radius must be equal to 30 over 2, that is 15. When you find the center of this circle, this point is point O. OA is of course the radius of the circle that is 15. OB is also the radius of the circle that is 15. And we join points P and U together. P and O together by straight line. PO is also the radius of this semicircle that is equal to 15. In the next step we completed this semicircle to a circle. And we extended the radius PO by straight line until it touches the circle at this point. So this is the touching point. The touching point of the extended radius PO with this circle. So we define this touching point as point M. In the next step we join points M and B together by straight line. Those two angles are defined as vertex angles, and we know that vertex angles are equal to each other. So if this angle is theta, then this angle must be also equal to theta because they are equal to each other according to the rule that I mentioned. In the next step we complete actually, we proved that triangle APO is congruent to this triangle OBM. So why those two triangles congruent to each other? First of all, PO equals to OM, the above the area of the circle, that equals to 15, therefore they are equal to each other. In addition, those two angles are defined as vertex angles, and vertex angles are equal to each other. And finally, side AO of triangle AOP is equal to side OB of triangle OBM. They are both the area of the circle that is equal to 15, therefore they are equal to each other. So we proved that those two triangles can go to each other according to side angle side rule. We have those two sides and the angle that is included between those two sides, that is angle theta, in triangle POA, that are correspondingly equal to those two angles and the angle, those two sides and the angle that's included between those two sides in triangle BOM. Therefore, those two triangles can go into each other according to side angle side rule. From the fact that those two triangles can go into each other, we know that side BA is equal to side MB. Side BA equals to side MB. According to the rule that corresponding sides that can go into triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides PA and BM must be equal to each other. But PA equals to 10 according to what is given as the equation. So PA equals to 10, from this equation 10 equals to PA equals to BM. We derive that BM also equals to 10 units in its length. This is side BM is also equals to 10 units in its length. Okay, so we know that chord PM passes through point O, that is the center of this circle. We know that any chord that passes through the center of the circle must be the diameter of the circle or semicircle. So PM is the diameter of the semicircle, so according the semicircle with the diameter of PM, and you can analyze this semicircle with the diameter of PM. So okay, this is the semicircle with the diameter PM, the diameter of the original domain. We know that PQ equals to 10 units in its length, MB equals to 10 units, point O is the center of the semicircle, and QB equals to X. That is the line segment that we are looking for in this question. In the next step, extended side PQ by straight line and side MB also by straight line until they touch each other at this point. So we define the touching point, this point is point E. By doing these constructions, we're going to do triangle PEM. This is triangle PEM. PQ equals to MB equals to 10. So QE must be equal to BE. QE must be also equal to BE because of the fact that PQ equals to MB. When you extend two equal sides by straight line, the result must be that the QE must be equal to BE because PQ equals to MB. And therefore, the extended sides QE and BE must be also equal to each other. So if QE is y, then PE must be also equal to y. So in total, EP equals to 10 plus y, and EM also equals to 10 plus y. Therefore, side PE is equal to side ME. Therefore, triangle PEM is an isosceles triangle, and we have the rule that in front of equal sides in the triangle there are equal angles. So in front of this side EP we have this angle, in front of this side EM we have this angle. And because of the fact that those two angles are located between, in front of those two equal sides, they must be also equal to each other in their sizes. So if the size of this angle is better, then the size of this angle must be also equal to each other according to the rule that I mentioned. So in the domain we have, this is quadrilateral PQMB. This quadrilateral PQMB is inscribed by this semicircle. If we complete the semicircle to a circle, then this quadrilateral PQBM will be inscribed by a circle. So therefore, you can say that quadrilateral PQBM is inscribed by a circle. And we have the rule that any quadrilateral that is inscribed by a circle, then its two opposite angles, the sum of its two opposite angles must be equal to 180 degrees. So because of the fact that this quadrilateral PQBM is inscribed by a circle, the sum of its two opposite angles must be equal to 180 degrees. Those are the two opposite angles of quadrilateral PQBM. and the sum of those two angles must be equal to 180 degrees. But this is angle beta. So angle beta plus this missing angle, in total the sum of those two angles must be equal to 180 degrees. Therefore, this missing angle must be equal to 180 degrees minus beta. Why? Because 180 degrees minus beta plus beta is 180 degrees. That is the sum of the angles in a quadrilateral. The sum of the opposite angles in a quadrilateral that is described by a circle. Therefore, this missing angle equals to 180 degrees minus beta. Likewise, according to the sum rule, angle beta plus this missing angle must be equal to 280 degrees. Therefore, this missing angle must be equal to 180 degrees minus beta. So, in total, we found out that this is angle beta, this angle equals to 180 degrees minus beta. 180 degrees minus beta plus beta is 180 degrees. So the sum of those two angles is equal to 180 degrees. But those two angles are defined as one-sided interangles. Thus we found out that the sum of those two one-sided interangles is equal to 180 degrees. And according to rule 18, if we have two one-sided interangles that the sum of them is equal to 180 degrees, then they must be located between parallel lines. Therefore, those two angles, the sum of those two angles is 180 degrees, must be located between parallel lines. That is to say, according to rule 18, line QB is parallel to line PM. Okay? Line QB is parallel to line PM according to rule 18. QB is parallel to PM according to rule 18. So in the next step, I copied the semicircle P with the diameter PM in a new page, and we continue to analyze this semicircle. So this is the semicircle that I copied on the original drawing with the diameter PM. Point O is the center of the circle. PQ equals to 10, QB is X, and BM is 10. We join points O and B to on Q together by a straight line. OQ is the radius of the semicircle that is 15. We join points O and B together by a straight line. OB is also the radius of the semicircle that is 15. OP is the radius of the semicircle that is 15, and OM is also the radius of the semicircle that is 15. We already found out that according to rule 18, side QB is parallel to side PM. Again, according to 18, side QB is parallel to side PM. And because of the fact that those two angles are located between the parallel lines QB and PM, and they are alternating angles that are located between the parallel lines QB and PM. And according to rule 15, alternating angles between parallel lines are equal to each other. And because of the fact that those two alternating angles are located between the parallel lines QB and PM, they must be equal to each other. So if this is angle alpha, then this angle must be also equal to alpha according to rule 15. In the next step, I copied the green triangle PQO in a new page and implemented the law of cosines in this green triangle PQO. So I click quickly on the law of cosines. The law of cosines is true in any triangle. This is triangle ABC that could be any triangle. In this triangle ABC, side AB equals to A unit in its left, side AC equals to B unit in its left, and side BC equals to C unit in its left. This is angle theta. So according to the law of cosines that is true in any triangle, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. Again, cosine theta equals to A squared plus B squared minus C squared over 2 times A times B. So actually, this is the green triangle PQO that I copied from the original drawing. According to the law of cosines, in this triangle PQO, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. Again, cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. So this equation is the implementation of the law of cosines, and this triangle PQO. In the next step, I copied this triangle QOB in the equation, we implemented the law of cosines in this triangle QOB. According to equation 1, we only found out that in the green triangle cosine alpha equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. This is triangle QBO that are coming from the original domain. In this triangle QBO, according to the law of cosines, cosine alpha equals to x square plus 15 square minus 15 square over 2 times x times 15. Again, according to the law of cosines, in this triangle QBO, cosine alpha equals to 15 square plus x square minus 15 square over 2 times 15 times x. So we have two different equations for the value of cosine alpha. Again, this is the first equation for cosine alpha, and this is the second equation for cosine alpha. Therefore, we created equation 3 that says that cosine alpha according to equation 1 must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 1 equals to 15 square plus 15 square minus 10 square over 2 times 15 times 15. And it must be equal to cosine alpha according to equation 2. Cosine alpha according to equation 2 is 15 square plus x square minus 15 square over 2 times 15 times x. So we have 2 times 15 in the denominator of this expression. We have also 2 times 15 in the denominator of this expression. So 2 times 15 will get cancelled. And we have here 15 square minus 15 square is 0. So in the denominator of this expression, we have only x square over x. X square over x is x. And in this side of the equation, we have 15 square plus 15 square minus 10 square over 15. So in total, we found out that x equals to 15 square plus 15 square minus 10 square over 15. X is the line segment that we are looking for in this question, so x equals to 15 square is 225, so 225 plus 225 is 450, minus 10 square. 10 square is 100, so in the numerator we have 450 minus 100 divided by 15. 450 minus 100 is 450, so in total this expression equals to 350 over 15. Here we divided both the numerator and the denominator of this number by 5. So 350 over 5 is 70, as 15 over 5 is 3. So in total we found out that x equals to either 70 over 3 units in itself, or 70 over 3 is 23 and third. So we found out that the length of this line segment QB is equal to x, it is equal to either 70 over 3 units, or QB is equal to x is equal to 23 and third units in its length. Okay, thank you very much.